Welcome back. In this lecture, we will discuss error minimization in linear regression. So our main objective here is to understand error minimization, specifically around calculating the mean squared error. Now let's start out with the key assumption that is being made in many of these supervised machine learning models. And there are n samples. And as we discussed earlier, these capital X's, those are the feature vectors associated with each of the n samples. We're going to assume that each of these samples is independent and identically distributed, IID. Now, what does that mean? Well, that means that number one, each sample is independent, so they're selected from the same domain, but they're not dependent on the selection of the other samples. So it's not like I change something about the data by picking a sample that now causes something to be different in the next sample that I select. No. Everything is like being drawn out of the same hat, and it's not causing any knock-on effects of the other samples. The next is identical, and this refers to that each sample is drawn from the same distribution. There's no change in the distribution that produces these samples. Now, this is an assumption. It's not always true, or it's true to varying degrees. And in real life, when we have machine learning models that operate within a company or a government system, the distribution of the data inevitably will change over time, and it will cause this assumption to be violated somewhat. One of the key tasks with machine learning operations is to understand when we move too far away from the assumption stated on this slide. So, some key questions. Getting back to our regression model, we need to find a vector W. Remember, W is our vector of the parameter weights for our f function so that it's as close to the test set as possible. But how do we measure the closeness to the test set? Well, some of you may already have guessed by our lesson objective, and one way to do that is to minimize the mean squared error. So what is the mean squared error? Well, we have these samples, these x vectors, and we have a function, fwx. Now, here, the thing that we're searching for is not x, but w. Okay, so bear that in mind. So even though it's not the argument of the function, that's the thing we're actually thinking about here. Now we also have an n-sized ground truth vector. Now this is n. Remember, m is the number of features. N is the number of samples. So this vector is the size of the number of samples, and this is vector y. And component yi, so this is a single value, it corresponds with the ground truth target value for sample xi. So if we think about a single spreadsheet that has all of our feature values, male, female, age, other demographic information about our diabetes patient, and then we have that target value, that quantified level of risk for disease progression. That last column, that's the yi. So what we've done with that spreadsheet is we've separated that one column out in its own vector, because that's what we care about comparing our results to. So the mean squared error, all this is just the square of the difference between the predicted value, which is fwxi, and the actual value, the yi. And we take the square of it because we want to avoid having to deal with sometimes it's higher, sometimes it's lower, so we have this positive negative thing. You don't want that because that would give us some weird results, so we square it. Now, the thing is we're looking for W. So it's more than just calculating the mean squared error. We got to find that parameter that causes that function to minimize the mean squared error. That's what we care about here. So keep that in mind as we go through this. Now, mean squared error during training, like I said, this is what we're looking to optimize. during testing, we just can use it to calculate directly as an evaluation metric, just like in other things like in classification, we have stuff like precision and recall. We can look at mean squared error as a way of evaluating. So here is a very simple and honestly not that great of a regression model for one or two of the features in our diabetes data set. So here we have the line resulting from or just from one feature rather, normalized age. We have the line that's learned from fitting normalized age to the quantified measure of disease progression. Now we went with one variable here just so I can show you what it looks like visually. So we compare the predicted and actual values, so we have this difference. Okay, notice some of them are positive, some of them are negative. And then we just take the square of that and we sum it up. And that's how you calculate mean squared error. It's that simple. Now, this says nothing about how we're using it to actually go about finding the weights. So, again, what we're doing is we're solving an optimization problem. So we want to find a W such that this function here is minimized. So there's a method called least square solution. And the idea is you're going to take the derivative of the mean squared error, but with respect to W. So this is a key thing in machine learning because right away, most of you will look at, oh, it's a function f of x, so I want to take the derivative with respect to x. No, you don't want to do that because if you go back, remember that the x here corresponds with the samples, and we already know all those values because we're summing over the measurement for all the different samples. So we're not finding the derivative with respect to x. We're finding it with respect to W. And we set this derivative to 0. Why? Because remember, derivative is the slope of the tangent line. And if it's 0, and we assume a concave function, then that will be a minimum point, assuming that it's a global minima. So then what you can do is you can solve for W using linear algebra. And again, this is why it works. You have no slope. But there's some issues with this. So first is this does not scale to larger size data sets. And based on the size of the features or the size of the data itself, this is running in either number of samples in the historical data multiplied by the features squared, or a quadratic of the number of features, so whichever one dominates. So that doesn't scale very well. And so what ends up being used in practice is a technique called gradient descent. And actually this is like the workhorse of machine learning. It's not only used for regression problems, but it also gets used for things like neural networks, gradient boosted decision tree, and many other things like logistic regression as well. So thank you for tuning in to this lecture on error minimization. Please stay tuned for more content.